In this video, we give a quick introduction to the squeeze theorem and the geometric intuition behind the squeeze theorem. Then we cover several examples of how to apply the squeeze theorem. As part of our examples, we'll also introduce the idea of an envelope that modulates a sinusoidal function. And this is just another way of talking about the functions that are doing the squeezing. So we start things out with a statement of the squeeze theorem, but I want to focus first on the picture that captures the geometric meaning of this theorem. The whole idea is that you have two functions that are known to go to the same limit at x equals a. And if you have a third function trapped between these two original functions, that third function has no choice but to go to the same limit. So we say it's being squeezed between the two original functions and forced to go to that same limit. And this gives us a powerful tool for proving a variety of limits, in particular when part of the function we're studying is sinusoidal, as we'll see in the examples. So to read through this theorem real quick, we have three functions, f of x, g of x, and h of x, defined on an open interval containing a, but not necessarily at a. And that's because the definition of these functions at x equals a is irrelevant to their limit there. And then we get really the key piece of information here. The function g of x is trapped in between f of x and h of x. So we express that as a compound inequality. F of x is less than or equal to g of x, but g of x is less than or equal to h of x for all x in this open interval. So if the limit of f of x and the limit of h of x, as x goes to a, both approach the same value of L, then g of x approaches that same limit as well. So that's our basic idea. If we're trying to compute a tricky limit and we can express the function as being trapped between two simpler functions whose limits agree, then we can compute our limit using the squeeze theorem. So here's our first example of a squeeze theorem limit. We have the function x times cosine x, and we're trying to take the limit as x goes to 0. And the reason the squeeze theorem is so useful with sinusoidal functions, I mean the sine or the cosine, is that we know there's a lower bound and an upper bound to a sinusoidal function. The cosine function is always between -1 and 1. So that's going to be our starting point here to try to get a handle on what the simpler functions are that we might use to squeeze this guy. So there's our starting point. The cosine function is trapped between -1 and 1 always. So in the case that x is greater than or equal to 0, in other words, x is non-negative, it's pretty quick to come up with lower and upper bounds on the function we're trying to take the limit of. All I have to do is multiply all three sides of this compound inequality by x, and because x is greater than or equal to 0, it's not going to tamper with the direction of the inequalities. So there it is, x cosine x is bounded below by -x and above by x, and those will be the squeezing functions, but it only counts for when x is greater than or equal to 0. If x is less than 0, we have to state a separate case. In that case, it reverses the direction of the inequality signs because we're multiplying by a negative. So I end up with -x greater than or equal to x cosine x greater than or equal to x. Now we can reverse the direction of that second inequality. If -x is bigger than x cosine x and x cosine x is bigger than x, it's totally equivalent to just say x is less than or equal to x cosine x, and x cosine x is less than or equal to -x. Again, that's only true if x is a negative number. So now we look at these two inequalities that we've produced. If x is non-negative, we get the one on top, and if x is negative, we get the one on the bottom. And on the left side of this compound inequality, that -x in the first inequality is guaranteed to be a negative number with a magnitude of absolute value x. If I look at the bottom inequality, again, because that's the case where x is negative, this is a negative number with a magnitude of absolute value x. So we can rewrite this in terms of a single function. The lower bound for x cosine x is going to be negative absolute value x. Now similarly, the right-hand side of each compound inequality is guaranteed to be a positive number. It's x when x is greater than or equal to 0. It's -x when x is less than 0, but -x is a positive thing if x is less than 0. So on that side of the compound inequality, we find that x cosine x is less than the absolute value of x. Now what we've done there is find an upper bound and lower bound for x cosine x that's valid for all values of x. So this is going to cover the left side and the right side of the limiting point that we're investigating. So recall that the absolute value of x is this v-shaped function. And the right side up, v, that's the absolute value of x, and the upside down v, that's the negative absolute value of x. So there's the upper bound and lower bound functions for the squeeze theorem. And I want to point out that we can also call that a modulating envelope for the cosine function. Or another way to say it is that the cosine function is modulated by this envelope. So we see that the limit of the absolute value of x as x goes to 0, that's going to be 0. And it's the same for the negative of the absolute value of x. So just to wrap up the application of the squeeze theorem here, we say the limit of the absolute value of x as x goes to 0 is 0. And the limit as x goes to 0 of negative absolute value of x is also 0. And this implies, because those are upper and lower bounds for our function, this implies by the squeeze theorem that the limit of x cosine x as x goes to 0 is also 0. Our next example is actually a little bit easier case because we don't have to worry about separating it into two cases where x is non-negative and where x is negative. This time it's the limit of x squared times cosine x as x goes to 0. And we start again by mentioning the lower and upper bounds for the cosine function itself. The cosine is always between -1 and 1. And now I can just multiply all three sides of the compound inequality by x squared, which is always positive. So we can just do this in one step. And we find that negative x squared is less than or equal to x squared cosine x, and x squared cosine x is less than or equal to x squared. So the function of interest here is always bounded between negative x squared and positive x squared. So there's the lower and upper bounds for our function of interest. And again, typically when there's a trig function involved, we can use this idea of a modulating envelope. So we're saying that this cosine is being pinched to 0 by this envelope that's made of a right side up and upside down parabola. And of course, the limit of x squared and the limit of negative x squared as x gets close to 0, those are both 0, so they squeeze x squared cosine x to that same limit. So to write our little squeeze theorem proof, we say the limit as x goes to 0 of negative x squared is equal to 0, and the limit as x goes to 0 of positive x squared is equal to 0. And because those are lower and upper bounds for our function of interest, the limit as x goes to 0 of x squared cosine x is equal to 0 as well. Our final example is a little bonus because we're getting into limits at infinity earlier than most calculus textbooks would do it. But these sorts of limits are actually really common in physical applications to physics and engineering, so I like to introduce them as early as I possibly can, and they're pretty intuitive. In this one, I have the limit as x goes to infinity, in other words, as x becomes large, of e to the negative x times cosine x. Well, e to the negative x is a decaying exponential function. So that's going to force this expression to become very small as x becomes large. Intuitively, I can just see immediately the limit must be 0 because I have a finite thing, that's the cosine x, being squished to 0 by a decaying exponential. Now to be a little more formal about it, we start again with the lower and upper bounds for the cosine function, and this will be similar for a sine function. And then we multiply all three sides by e to the negative x, so we can get lower and upper bounds on our function of interest. So our lower bound is negative e to the negative x, and our upper bound is e to the negative x. And we see in the graph that our function is never going to exceed that upper bound of e to the negative x, and it's never going to go below that lower bound of negative e to the negative x. It will actually periodically touch these upper and lower bounds. That happens when the value of the cosine function is 1 or -1, but it never goes beyond these limiting values. And again, we're going to say that this cosine function is modulated by a decaying exponential envelope. So to wrap things up with the squeeze theorem, we have the limit as x goes to infinity of negative e to the negative x. That's equal to 0. And if that isn't clear, we can throw in one extra step here and just point out that e to the negative x is 1 over e to the x. And e to the x gets large very quickly as x increases. So I have 1 divided by this infinite thing, which gives me 0. So there's my lower limit. Now for my upper bound of e to the negative x, it's the same issue. I have 1 over e to the x, but 1 over an infinite thing is going to give me 0. So because our function is always trapped between this lower and upper bound, and the lower and upper bounding functions both go to 0 in the large X limit, we conclude by the squeeze theorem that the limit of our original function is 0 as well. Now I want to point out that this example was not completely rigorous because the way the squeeze theorem was defined was for a limit approaching some value a, and then I had functions defined on an open interval around a, and infinity is just not some finite value. So things are a little bit different here. But we'll get back to formally expanding the squeeze theorem to handle this case a bit later in the course. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.